Greetings, fellow seekers of knowledge. Welcome back to Beyond Sci Convo. Today we embark on a journey into the depths of physics to unravel the enigma of touch. Have you ever pondered why, despite the illusion of contact, we can't truly touch anything? Brace yourselves as we venture into the microcosmic world of atoms, electrons, and the dance of forces that govern our tactile experiences. To comprehend why we can't touch anything, we must first delve into the building blocks of matter, atoms, and molecules. Our world, from the table to our skin, is composed of these minuscule entities engaged in an intricate dance. When your hand approaches the table, it's not a direct contact, but rather an interaction between the outer electrons of the atoms on your skin and those on the table's surface. The Pauli exclusion principle, a fundamental concept in quantum mechanics, plays a pivotal role in this dance. Electrons, those elusive subatomic particles, have a peculiar aversion to sharing the same quantum state. As you attempt to bring your hand closer to the table, these electrons repel each other, creating an invisible barrier that prevents true contact. Enter the electromagnetic force, the invisible hand that shapes the interactions between charged particles. The electrons, being negatively charged, experience a force of repulsion when brought into proximity. Imagine two positively charged magnets, resisting each other's pull. This electromagnetic repulsion is the reason why your hand doesn't seamlessly merge with the table's surface. Now let's introduce a mind-bending concept, quantum tunneling. Despite the barriers imposed by the electromagnetic force, there exists a minuscule probability, dictated by quantum mechanics, that electrons can traverse these obstacles. It's as if they execute a ghostly handshake, momentarily bypassing the repulsion forces. To appreciate the rarity of quantum tunneling, we must delve into the mathematics of probability. Quantum tunneling involves the wave-like nature of electrons, where their wave functions overlap, allowing them to exist in regions that would otherwise be forbidden. The probability amplitude of finding an electron on the other side of the barrier is non-zero, albeit incredibly small. Our exploration wouldn't be complete without a nod to Werner Heisenberg's uncertainty principle. This fundamental concept in quantum mechanics states that it's impossible to simultaneously know the exact position and momentum of a particle. The uncertainty surrounding an electron's position adds another layer of complexity to the intricacies of touch. As we unravel the mysteries of touch, quantum mechanics emerges as the protagonist in this cosmic drama. The subatomic realm challenges our conventional understanding of reality, inviting us to marvel at the paradoxes and probabilities that govern the fabric of the universe. Let's draw some connections between touch and the fundamental forces governing our universe. We've explored electromagnetism, but what about the other three forces? Gravity, the weak nuclear force, and the strong nuclear force. While gravity is a dominant force on larger scales, it's negligible at the atomic level. The weak and strong nuclear forces operate within atomic nuclei, contributing to the stability or decay of particles. Although gravity may seem distant in our exploration of touch, it plays a subtle role in shaping our tactile experiences. The weight of your hand and the table, influenced by gravity, adds a gravitational force to the interaction. However, the electromagnetic forces take center stage, overshadowing the gravitational pull on the atomic scale. Zooming in further, we encounter the strong nuclear force, binding protons and neutrons within atomic nuclei. The weak nuclear force, responsible for processes like beta decay, is less influential in our everyday tactile encounters. As your hand approaches an object, you're essentially investing energy to overcome the repulsive forces between electrons. This energy is stored in the potential energy of the system, emphasizing the interconnectedness of touch and the fundamental principles of physics. Energy conversion adds another layer to our exploration. When your hand makes contact with the table, the kinetic energy of your moving hand transforms into potential energy as the electrons repel each other. This interplay of energy conversion underscores the dynamic nature of touch as a complex interplay between motion and potential. This explains the law of conservation of energy and matter. That is, energy neither be created nor destroyed, but it can transform from one source to the other. Now, let's focus on the unsung hero in our tactile experiences, our skin. Skin serves as the interface between our bodies and the external world, equipped with sensory receptors that convert physical stimuli into electrical signals. The topmost layer, the epidermis, shields us from the environment, while the dermis houses nerve endings and blood vessels. As we touch an object, the pressure exerted on our skin activates mechanoreceptors, specialized neurons responsible for detecting mechanical stimuli. These mechanoreceptors generate electrical signals that travel along nerve fibers, ultimately reaching the brain. The brain interprets these signals, translating them into the tactile sensations we perceive. Let's explore the role of the brain in crafting the illusion of touch. The brain receives a barrage of sensory information from various parts of the body, integrating and processing these signals to construct our perception of the external world. Touch, in essence, is a multisensory experience shaped by the brain's intricate processing capabilities. Brain's interpretation of sensory information adds a layer of subjectivity to our tactile experiences. Factors such as attention, expectation, and even cultural influences can shape how we perceive touch. This subjective nature underscores the complex interplay between the physical reality of touch and our cognitive interpretation. Temperature, an often overlooked aspect of touch, significantly influences our tactile experiences. When we touch an object, we not only perceive its texture but also its temperature. The flow of thermal energy between our skin and the object further enriches the complexity of touch, creating a holistic sensory experience. As we broaden our horizons, let's ponder touch in microgravity environments, where the conventional rules of touch are disrupted. In the absence of gravitational forces, touch takes on a different character. Microgravity experience a unique form of touch. Without the constant force of gravity, the subtle interactions between atoms become more pronounced. As they reach out to touch objects, the absence of a dominant gravitational pull allows electromagnetic forces and quantum effects to take center stage. In microgravity, atoms exhibit a different dance, influenced more by their inherent properties and less by the downward pull of gravity. The delicate interplay of electromagnetic forces gains prominence, offering a glimpse into the pure essence of atomic interactions without the interference of gravity. Now let's elevate our perspective to the cosmic scale. Beyond our earthly experiences, touch takes on new dimensions in the vastness of space. Objects in space, devoid of a tangible surface, challenge our conventional understanding of touch. Can we touch the stars or the void between galaxies? In the cosmic dance, gravity reigns supreme on the grand scale, orchestrating the movements of celestial bodies. The touch of celestial objects becomes a gravitational affair, binding galaxies, stars, and planets in an intricate cosmic ballet. The electromagnetic forces still play a role, but on this expansive stage, gravity takes the lead. As we contemplate the limits of touch, we encounter scenarios where the traditional sense of touch becomes elusive. In the vacuum of space, devoid of a medium for transmission, the very concept of touch undergoes a metamorphosis. Astronauts floating in the void may perceive touch differently, relying more on visual and tactile feedback from their spacesuits and equipment. Bringing our cosmic exploration back to Earth, let's redefine touch in the context of our daily lives. The illusion of contact persists, but now, armed with the knowledge of atomic interactions, quantum effects, and the cosmic dance of forces, we appreciate touch as a dynamic interplay of fundamental principles.
In conclusion, the enigma of touch takes us on a journey from the microscopic world of quantum mechanics to the cosmic expanses of space. We've unraveled the intricacies of atomic interactions, delved into the sensory realm of perception, and contemplated touch in the vastness of the cosmos. As fellow seekers of knowledge, let's continue to embrace the enigma of touch, recognizing that our tactile experiences are not only influenced by the forces within our immediate surroundings, but also by the cosmic forces that govern the universe. In the grand tapestry of existence, touch remains a captivating and ever-evolving mystery, inviting us to explore the boundaries of our understanding and marvel at the wonders that lie within and beyond our reach. Keep reaching for the stars, both figuratively and literally, in your quest for knowledge. And before we end this fascinating journey, don't forget to like, share, and subscribe.